this video, we're going to look on Excel loaded members. In another section, we're going to look on statistical indeterminate problems. We're given a question. A steel tube is fitted around a solid aluminum cylinder as shown below. So this is the diagram. The assembly is compressed between rigid plates by central applied forces. We're going to see F here and F here, and the compressive forces. The aluminum cylinder is 70 millimeters in diameter, and the steel is an inside diameter of 80 millimeters and an outside diameter of 100 millimeters. If the force which is being applied is 240 kilonewtons, find the stress in the aluminum and the stress in the steel. And we're also going to find the change in length of the assembly. We're given the young modulus of steel and the young modulus of aluminum. I'm going to show you how to solve this question using two methods. What we always do, we have to first draw a free body diagram. We have the force F, which is acting, and we are told that the magnitude of that force is 440 kilonewtons. So it's been compressing and also compressing on both ends. That means we're going to give a reaction, an opposite reaction inside. So it's coming from the steel and from the aluminum, and also you have our length, which is 200. Then I have drawn the cross-sectional view. You can see we have a steel, which is the aluminum, which is inside at the core, and also you have the steel, which surrounded the aluminum. So what we're going to do, first of all, we're going to write the given data first. We're given F, which is 240 kilonewtons. We're given the diameter of the aluminum, which is at the core, which is at the center. So I'm going to write DA right here, which is 70 millimeters. But on the steel, we have the inside diameter and the outside diameter. So I'm going to write DS1 for the inside diameter, which is 80 millimeters. And I'm going to write DS2 for the outside diameter, which is 100 millimeters. Also given the young modulus of steel, so I'm going to write ES here, which is 210 gigapascal. And I'm going to given the elasticity, the young modulus of aluminum, which is 70 gigapascal. Just write the length. So the length is equal to 200 millimeters. But I think you've noticed, since this one is a cylinder, you know the length is going to be the same from here to here. So that means the length LS and LA should be equal to L, also the same. And the other thing that we're going to need the area. So let's start by finding the area okay, since I've write AS here, let's find the area of the steel. So the area of the steel is going to be the upper part of the steel minus lower part to find. So I'm going to deduct these two areas, the area of the whole circle minus the area of this region. So it's going to be pi radius squared, but in this case I given diameter, so it's going to be pi over 4, and I'm going to subtract d2 squared minus d1 squared. And if we do this, we're going to find the area to be pi over 4 and going to be 100 millimeters squared minus 80 millimeters squared. And if we do that, we're going to get 900 pi millimeters squared. And now let's find the area of the aluminum, which is going to be pi over 4, and this is going to see the diameter. We have the radius, so it's going to be diameter divided by 2 squared. So I'm going to write d squared, and this one is dA. It's going to be pi upon 4. What is the diameter? The diameter is 70 millimeters squared. And if we do that, we're going to get 1225 pi millimeters squared. Okay, so now we have the information that we need. Let's start to solve this problem. So what we are going to do, first start by writing the equilibrium equation. On the equilibrium equation, I'm just going to use Newton's third law of motion. Action equals to reaction. So what do we have? I'm going to start by taking the cross section. I'm not going to take the whole part, so I'm going to take that. So I'm going to have a reaction which is R here, but that reaction, you know, it's going to come from the steel and the aluminum. The equilibrium equation, what I'm going to do, I'm going to resolve along the x-axis. So I'm going to solve along the x-axis, and the total sum of the force should be equal to 0. And I'm going to take my right. As the positive. Okay, so you have to be very careful when resolving. People have been asking me questions about the sign, so you have to make sure that if you are resolving from the right to the left, from the left to the right, you know, any opposing force will be treated as a negative. So now what we're going to do, we know, since this is the cross-sectional area, this is the cylinder, and this is the steel, and this is the aluminum. So what is going to happen? You know that action equals reaction. So I'm going to have a negative force, 240 newtons, which is F. and R is going to be positive. So that means R, positive R minus F, that should give us 0. But let's take a closer look at R. R is the sum of the force being exerted by the aluminium and the force being exerted by the steel. So it's going to be FA plus FS minus F, and that should give us 0. And if we arrange this, we're going to see that FA plus FS should give us F, and we're going to call this equation number 1. See, we have one equation and we have two unknowns, so we're going to need another equation, and the equation that we're going to use is the compatibility equation. Okay, so on the compatibility equation, we know the aluminium and the steel, they are rigid, they are attached to each other, so the total change in length is going to be the same. So that means the total change in length of the steel should be equal to total length of the aluminium. Okay, and after that we're going to look on the force displacement relationship. Okay, so this is the second equation. There's going to be a change in length due to force. So no, the change in length of the steel is going to be the force which is being applied on the steel, and that force is FC. That is going to be the reaction force right here of the steel, right? It's going to be a reaction force here, so it's going to be FS. It's going to be FS times the length of the steel divided by area of the steel times the Young modulus of the steel, and I'm going to call this equation number 3. And the change in length of aluminium is going to be force, which is going to be FA, and the length is going to be LA divided by area of the aluminium times the Young modulus of the aluminium. I'm going to call this equation 4. So now we have 1, 2, 3, 4 equations, and we have two unknowns. So I think if we draw algebra here, we can solve them. So I'm going to write from equation 2, although that the change in length of steel and the change of length of aluminium should be the same. So that means equation number 3 should be equal to equation number 4. So you can write FS LA here, AS ES should be equal to FL LA AA, and we're going to have EA right here. Okay, so we have to make either FA or FS as the formula. So I'm going to make FS. So it's going to be FS, and I'm going to multiply both sides by AS and E. But we know that the length is the same from here, so you can just cancel it. So I'm going to have FA, and I'm going to have AS, and I'm going to have ES divided by AA, and I'm going to have EA here. I'm going to call this equation number 5. Right? So let's take a closer look at equation number 5. You can just write FA right here. AS is the cross-sectional area of the steel, and A is the cross-sectional area of the aluminium. So since it's just division, you can just use the millimeters here. So what we're going to have here on the area of the steel, the area of the steel is 900 pi times Young modulus of the steel, which is going to be 210, and still have Young modulus on the upper bound and upper bound. We're no longer concerned about the giga. It's going to cancel each other, and we're going to have times the area. So the area of the aluminium is 1225 pi times the Young modulus of the aluminium, which is 70. And if we simplify here, we're going to get FA. And you're going to have 108 over 49, right? So FS equals to FA times 1/8 over 49. Okay, then now we're going to sub FS into equation number 1. So what is equation number 1? That is the equilibrium equation. We know if we say FA plus FS minus F should get 0, and we know FA, we have FA right here, plus, and for FS I'm going to write FA times 108 divided by 49, and that should be equal to 240 kilonewtons. 240 kilonewtons. We can factor out FA, so we're going to have FA, and we're going to have 1 plus 108 over 49 right here, equal to 240 kilonewtons. So that means FA is going to be 240 kilonewtons. I'm going to divide it by 1 plus 108 over 49. And if we do that, we're going to see that FA is going to be 11,760 over 157 kilonewtons. Okay, so I'm going to write it as a fraction. I won't leave it as a fraction in order to obtain some exact value. Calculating stress. From here, I know that you can calculate Fa. So from my equilibrium equation, or from this equation, you know that Fs is equal to Fa. So Fa is 1160.157 times 108 over 49. So this will be in kilonewtons. And if we do that, we're going to see that Fs is going to be equal to 259.20 over 157 kilonewtons. That is going to be equal to Fs. So now we have the forces which are acting on each material. So I'm going to start by calculating the stress that is in the steel. Stress in the steel is going to be the force that is being applied on the steel times the cross-sectional area of the steel. So the force, what is the force on the steel? We said is 25,920 divided by 157 kilonewtons. And I'm going to divide this by the cross-sectional area, A, which is 900 pi, times, in this case I'm going to change millimeters squared to meters, and you know that 1 millimeter is equal to 1 times 10 to the power negative 3 meters. So if you say 1 millimeter squared, you're going to square, you're going to have 1 times 10 to the power negative 6 millimeters squared. So it's going to be 900 times 10 to the power negative 6 meters squared. And if we do this, we're going to see that the stress is going to be 58.4 kilopascal. That's going to be the stress in the steel. And we're going to move on to calculate the stress in the aluminium. Force which is acting on the aluminium divided by the cross-sectional area of the aluminium, and the force on the aluminium said it's 11,760 divided by 157, and these are all in kilonewtons. And I'm going to divide it by the cross-sectional area, which is 12,225 times 10 to the power negative 6 meters squared. This I'm going to get that. I'm going to see that the stress is going to be 1119.46 kilopascal. Okay, so this is going to be the stress in the aluminium. And on the last question, we need to find the change in displacement of the assembly. So since the assembled board is rigid or static, that means the change in length of the steel should be equal to change in length of the aluminium. So you can just choose anything that you want, and I'm going to choose the steel here. The change in length of the steel is going to be force acting on the steel times the length of the steel divided by area of the steel times the cross times the Young modulus. So on the force of the steel is 25,920 divided by 157. Now I'm going to multiply this by 10 to the power 3 to change it to newtons. Now I'm going to multiply by the length. So the length is 200 millimeters, right? You can just change it to meters. So I'm going to write the length as 2 meters. That is going to be 0.2 meters. Now I'm going to divide it by the cross-sectional area. So it's going to be 900 pi times 10 to the power negative 6 meters squared. Now I'm going to multiply this by the Young modulus, which is going to be 210 times 10 to the power 9 Newton per meter squared. Okay, and if we do this, we're going to get our answer as 5.56 times 10 to the power negative 5 meters. That's going to be the change in length of the whole assembly. But since it's compressive force, it's compressing, so it's going to be shortened. You have to indicate that. Then if you find the change in the displacement if you use a aluminium tool. So on the next video, it's going to be the second method. Then after that, you're going to look on how this thing will behave when subjected to a temperature change. Thank you for watching.